me start recording. Okay, so this probably is going to be a little shorter than the other lectures that we have had, but let's see how it goes. So let me first remind you of what we were doing. So we were interested now after our adventures with CFT. We were interested in another application. You'd seen one application when we were thinking about string theory. Now you're going to see another where we speak about something, I mean, as we said earlier, something called the holographic principle. So we said that, if you wanted to understand quantum gravity, the usual ways of trying to quantize, say, field theories don't work here. So you need to think out of the box. And one of the ways that we had discussed earlier was that we go from, point-like objects to one-dimensional strings. And if you had put in the inputs of special theory of relativity, and if you had quantized this system, what you are going to get is a quantum theory of gravity. By that, we meant that in the spectrum of this theory, we are going to find a massless spin-2 object. Now, interestingly, I found some references about field theories with spin 2, and I'll share that with you. One of the very fun things, something that I didn't know before, is that I found that you can actually prove that the fact that we know that gravity is attractive. So this is something that you can actually prove with a spin-2 field. Okay, so I'll try and forward that particular reference to you guys, and yeah, it's a nice nice cute thing to see. So it's actually my friend Daniel Gromiller was giving some lectures in his course, so he's written it up. And I hear from him as he's also writing a book. So that book may be an interesting one to, read when it's out. Okay, so we wanted, so in that case, what we do, so in a quantum theory of, the quantum theory of gravity is essentially characterized by the fact that it will have a massless spin-2 field in it, okay? Massless because you want the interaction to have this infinite range. And okay, so that's what it is. So that was one of the things. So string theory was one of the ways that you could get at a theory of quantum gravity. There's another very, even more surprising way of trying to address this, and that is what is known as the holographic principle that we learned about last time. Some of you may be thinking that since the holographic principle has its roots in string theory, you shouldn't really call it something else. But I would like to, I'd like to propound the idea that, you can think of holography without saying anything about string theory. Okay, and so the string theory example that we have is an example for sure, and that works fantastically well. And all of the known things we think are embeddable in string theory, but you could also formulate this without string theory in the sense that you could say, as I say here, that a quantum theory of gravity in a certain space-time n is exactly equivalent to a quantum field theory without gravity in one lower dimension, and this lives on the boundary of the space-time n, okay? Where it links up to string theory is when you look at the famous, ADS CFT correspondence. There, the theory of, quantum theory of gravity that you are speaking about is a particular superstring theory that's called a type 2b superstring theory, and this lives on ADS 5 cross S5. And this is dual to particular, field theory. In this case, conformal field theory, which is n equal to 4 supersymmetric Yang-Mills theory. Okay, as I wrote out here, and as we remarked, this n equal to 4 supersymmetric Yang-Mills theory is actually an interacting quantum field theory that exhibits quantum conformal invariance. By quantum conformal invariance, I mean if you calculate its beta functions, then you'll find that its beta functions exactly vanish. Okay. And as I said at the end out here, ADS-CFT is a particular. So this is not just ADS-CFT. This is, if you wish, the Malla-Sena correspondence. There are other things. So this is ADS-5-CFT4. Okay. So this particular thing is a particular manifestation of the more general idea of holography. So you can so there have been examples where you have ADS 4 and CFT3 and so on, and people have tried to look at ways to deform this and go elsewhere. A large part of my research is also essentially trying to understand, if you have, instead of ADS, if you were to replace it with flat space, could you find a dual to some particular theory which is like that? And so, that's something, again, I thought I'd give you a brief glimpse of, but, we are too, we don't have much time in hand, but you could try and model the things in the same way. You're good to try and say that, some particular theory in the bulk is equivalent to some particular theory on the boundary. What is going to happen is the symmetries are going to be realized have to be the same. So the symmetries of the bulk have to be realized in the boundary theory, which is one-dimensional lower. As you see, this is sort of the making of the fact that you had to. So the field theories that we were looking at were invariant in say, if you're looking in 4 dimensions, were not only invariant under the usual ISO 3.1, the Poincaré group in 4 dimensions, but we also found that they had these extra symmetries, right? When we were looking at conformal field theories, they have these extra symmetries. So instead of ISO 3.1, this group became SO4.2, right? That's what happened in D equal to 4. So we have these extra symmetries. The idea is that the isometry group in the bulk is going to be the same as the sort of global group on the boundary theory. So that is going to be the way this particular correspondence works. And you can try to do similar things when you're going to replace, ADS, for example, by a flat space. So the question in that case would be, can you realize a field theory which has these symmetries of, maybe, if you're thinking of 5-dimensional flat space, you're thinking of something like a group like called, ISO 4.1, right? Instead of ISO 3.1 in 4 dimensions. But ISO 4.1, now you need to try and understand if you can figure out a way that you can write down a field theory which is actually invariant under ISO 4.1 in 4 dimensions instead of ISO 3.1. So that's sort of the things that I am interested in and we are trying to formulate. But so in a sense, what you have to do is that the isometry group in the bulk theory should be equivalent to the global group on your field theory. So the bulk theory lives in one higher dimension, the field theory lives in one lower dimension, and the matching of symmetries go like this. So that is the first step. We'll try and elaborate this a little bit more as I just go on to the next part of the talk. But last time around, we also tried to discuss, how we can motivate such a thing. Okay, in a sense, I started out by saying that some non-gravitational quantum field theories are in a deep way quantum theories of gravity. And again, by a quantum theory of gravity, we mean a theory that has a dynamic metric whose linearized equations of motion generate a massless spin-to field that we call the graviton. Now, apparently, this particular statement is directly in loggerheads with another thing that we know, which is the Weinberg-Witten theorem, which says any quantum field theory with a Poincare invariant conserved stress tensor does not allow any massless particles having momentum greater with spin greater than 1. Okay. Now, this clearly is an issue, and the way around this sort of hurdle is to understand that the graviton need not live in the same space time as the field theory. So this is sort of like how holography is allowing you to circumvent a particular I mean uh, theorem that seems to stand in your way. So how do we see this? How do we how did Tufte Susskind at first come to the idea of the notion of the fact that quantum gravity has to live in higher dimensions to be equivalent to a field theory? Now that comes from the fact that you have further hints of this from black hole physics. So think of a particular volume of space-time. That particular volume of space-time, the maximal amount of matter that you can pack inside it is going to be that which creates a black hole of the same of the same volume. Okay, so now remember, this may not be something that you have seen or done before, but you need to, maybe in your advanced GR course, you might have seen it or something, I'm not sure. Uh, but the entropy of a black hole is given not in terms of its volume, but in terms of its area. The area of the event horizon in Planck units gives us what the entropy of the black hole is. There's also this famous factor of 4, which is there. So now this particular thing defines a limit of maximal entropy in a theory of quantum gravity. Again, notice that this goes like the area of the black hole and not like the volume of the black hole. Okay, so this means that quantum theory of GR is very different from usual field theories. Okay, so as it happens, so it's very clear that a quantum gravity theory has many degrees of freedom less than quantum field theory without gravity, if both of them live in the same number of dimensions. So in order to make these degrees of freedom match, the quantum theory of gravity has to live in some dimensions which are higher. Okay, so this was essentially the main idea that was behind this holographic principle by Tuft and Susskind. All right, so that was the thing that stems from the fact that black holes have entropy equal to area by 4. Very good. Now suppose you have a field theory. How are you going to account for this extra dimension? One of the very natural things to do is to look at the Wilsonian approach to RG flows, and then this gives you a very sort of as I write, an elegant answer to what the extra dimension might be. Now you remember your RG equation, your beta function equation, right? So this particular equation just says that you can relate a field theory at a certain scale to the same field theory, but at another scale. You can call it the length scale or the energy scale. This means that we don't need to know about what the coupling is at any other scale to know how it is going. It is going to change, and this is sort of symptomatic of locality of space time, if you wish. So this leads to the idea that you can view this extra particular extra extra dimension as the energy scale, because things also have to be local in that particular uh, that that particular dimension. So this means that you can actually interpret this as an extra direction. And then what you do is that, now you have this particular expression. So you would be able to, in a sense, write down field theories. You can write down one field theory, and then you can argue flow it and get another field theory, and you can write down a whole space of field theories if you wish, and that is going to give you in a sense some particular theory which has an extra dimension which is labeled by the energy. What you can also do is that you can simplify this equation. You can simplify this equation and put the right hand side of this equation to 0. Okay, so if you do that, so what happens is that you have an extra symmetry in the game of x mu goes to lambda x mu. Now the energy scales, which has to be treated as this extra dimension, on just dimensional grounds, you will have to go as lambda inverse of you. Okay, you can now write down the most general d plus one dimensional metric with d dimensional Poincaré invariance, and this particular way of trying to scale things. So then that metric becomes something like this. Okay, and this I've said that this is easily recognizable by as ADS d plus 1. We will explicitly see this right now. Okay, so that is what we have. And so, in a sense, what we see is that conformal field theories in d dimensions should be related to a theory of gravity in ADS d plus 1. Okay, the best example that we have till date is this original Mallasena correspondence, where the duality is between this n equal to 4 supersymmetric Yang-Mills, which has a gauge group SUN, and type 2b superstring theory on ADS 5 plus S5. These are words that you do not know, and I don't really want you to pay too much attention to this. What I want you to actually remember is that this is essentially uh, saying that a quantum field theory, conformal field theory in 4 dimensions, something that you guys have learned in this course, is exactly equivalent to theory of gravity, which lives in this weird negatively curved antidistant spacetime. Okay, so that is what the link up is. So we could spend a whole 6 months or a year just trying to do this, but what I wanted to do in this class that I'm going to, in this sort of next half an hour or so, is that I wanted to give you a brief sort of taste of what this is. And many of the things will not be clear at first sight, but those of you who are interested, now I think you would have the sort of background to go back and read those books or read those research papers and go ahead with this if you so want. Okay. All right, so let's do this. Okay, so this is the first picture of ADS CFT that you can find on Google. So this is the inside of this bowl, if you wish. So that the inside of the bowl is where your string theory or gravity lives, and your CFT or the theory without gravity actually lives on the boundary of space-time. Okay, very good. So what is ADS? All right. So you can start off with the Einstein-Hilbert action. And you can, so here G is the metric, and square root G is minus square root G is the determinant, square root of the determinant of the metric. R is the Ricci scalar, lambda is the cosmological constant. So if you start off with this metric, as you guys know very well, and if you vary the metric, then you find the equations of motion as R bu nu plus minus half R g mu nu plus lambda g mu nu equal to 0. So these are the vacuum equations, right? I have not put any extra matter in the game. ADS is a solution to vacuum Einstein's equations with negative cosmological constant. So if lambda is less than 0, if you are looking at something which is called a maximally symmetric spacetime, which means that alpha beta mu nu is something like this, then the solution that you get by trying to solve these equations is what is called ADS. All right. We will see this. We will see this in more detail, and of course, once you have the metric, you can try to see that it actually solves Einstein's equations and gives a negative cosmological constant and so on. Those are going to be exercises for you to do. This is actually going to be something that I'm not going to sort of force you guys to do, because those who have suffered at my hands in maybe Math Methods 1 and GR have already looked at these things. All right, very good. Now, P plus 2-dimensional ADS space is represented by a hyperboloid. Okay. Now this hyperboloid is going to have an equation like this. Okay. You see that there are going to be, if you wish, two plus signs and P minus signs, and so this is, and we are going to embed this particular hyperboloid in a flat P plus 3-dimensional space with this metric. Notice that these has two sort of time directions out here. Again, I do not want to actually go into a great amount of details out here, but I'll sort of send you some particular references by which you can go and try to see what is happening. So this is a hyperboloid which is going to be embedded in something like this. Okay. All right. Now, as you can see, if it's a hyperboloid, if this is going to be the thing that is going to be the invariant of the structure, so it's very clear that the isometry of this particular space-time is going to be given by SO2 P plus 1. Okay, so the 2 is for these two signs which are plus, and the P plus 1 is for the xi squares which have another sign. I hope this is obvious, right? Is this obvious to everybody? So you see that we already are ending up with an isometry of a space-time which is SO2 P plus 1. Okay. So now, so what is going to happen? You can solve this equation by trying to put in x naught equal to r cosine hyperbolic rho cos tau, xp plus 1 as r cosine hyperbolic rho sine tau, and xi as r sine hyperbolic rho, and these sigma i's are sort of the coordinates on the unit sphere. Okay, so if it's just an ADS3, for example, then this guy is not there. And yeah, if you have to do some more, you just have to use things such that this actually goes through. Okay, so this this again is the usual stuff that you guys have to do. And so you can solve 7.6 by trying to put these things in. So this solves it. Okay, now what you want to do is you want to get an intrinsic metric on this on this hyperboloid. So for that, what you need to do is that you need to use equation 7.8 and plug it into the metric of the embedding space. So if you do this example, do this exercise, then what you end up with is ds squared is equal to, there's an r squared outside, and there's a cosine hyperbolic squared d tau, d rho squared, then sine hyperbolic squared rho into d sigma squared. Okay, this is going to be the metric. This is going to be the metric of, this is going to be the global metric of the ADS p+2 that we are interested in. You can obviously start with 7.9, and you can find out what the Riemann is, and from there what the Ricci is, and what the Ricci scalar is, and you can plug all those things in to see that this actually satisfies the Einstein's equation with a negative cosmological constant. And you'll also find that R mu nu lambda sigma is R times GG minus GG, right? So this is something that you can do explicitly. And so GG by GG, I've obviously omitted the indices. So you'll see that this is a maximally symmetric space-time as well, which is something that you could have already said by looking at what the isometric group is. If these are things that are not familiar to you, a first course in GR should have done these for you. If it has not, then I suggest that you just go back and look at that once more. But that's what the ADS2, ADS p+2 metric looks like. So now, why is this the global the global metric? So okay, so remember that this guy actually looks like this. Okay, so R goes to, rho goes to infinity, takes you out in these two directions, and the sort of compact direction is your the tau. Okay. So what happens is, if you take rho greater than 0 and tau to be in this region, then 7.8, this particular solution that you have, this is going to cover for you the whole of the hyperboloid. Okay, so that is why this rho, tau, rho, and sigma I, these are called the global coordinates of ADS. Okay, now notice that rho goes to 0. In that case, what you're going to be doing is that you will find that the metric looks like this. Okay, so that's just look back out here. So this term drops off to 1. This term just becomes rho squared. So as you can see, this particular thing has a topology of S1, which is given by the the tau across an R p+1. So you see that there is an S1. So this actually represents closed time-like curves in the tau direction. You've seen that the tau goes from 0 to 2 pi. Now, closed time-like curves is a bad thing, right? So if you have something like that in a, a universe that has something like that, you can go back in time, kill your own grandmother, and then it's going to be so causality and things like that will just go out of the window. So we do not want any space times that have closed time-like curves. So in order to maintain things like cause and effect. So if you want a causal structure in your space-time, we just simply unwrap this particular circle, and you take tau to be between minus infinity and plus infinity with no identifications. This is called the universal covering of the hyperboloid, and does not now have any closed time-like curves. I could go on a lot more about this, but with some work, you can actually show that the boundary of ADS P plus 2 is a flat P plus one dimensional space. This requires a little more structures and little more work than I thought that I would be able to fit into this lecture. But again, this is reasonably straightforward, and you can see that this is going to happen. So what is happening, what will be happening is that the isometries of ADS will now act as conformal symmetries on the boundary. Okay, now for each of these things you would have an action, so you can look at the isometries, you can look at what they do, and you can take them to the boundary of the space, and there you would be able to see that those particular isometries act like some of the all of the sort of conformal isometries that you have seen. So in order to make this a little more transparent, let me try and take you to another coordinate system that you guys have already seen earlier, but let me try and clarify this. Now you remember that you had this particular hyperboloid, right? You had this particular hyperboloid, and you had one sort of way of trying to parametrize this hyperboloid was like this, and that led to a metric which had this, and this was sort of like what is called the global metric. Okay, and it's global because it covers the whole of whole of the hyperboloid. Now we are going to look at another sort of solution to this equation, and that particular thing will not be enough to cover the whole of the hyperboloid, but it will actually cover a certain patch of the hyperboloid, but it will also have its uses. So remember, if you remember from your black hole lessons, if you wish, that if you were thinking about the Schwarzschild, then there were several separate sort of coordinate systems. Sometimes this covered one region, did not cover another region. And there were lots of things, like there was the Schwarzschild coordinates, there was the infalling Eddington-Finkelstein coordinates, there was the outgoing Eddington-Finkelstein coordinates. These covered separate sort of patches, and then you had one of them which was called this Kruskal extensions, which actually gave you one single coordinate that would cover the entire space-time. Here, the thing that we have out here actually covers the entirety of ADS, but we will find it useful to look at something that does not do this. Okay. So for this, what we're going to do is we're going to look at this particular parametrization that we have here. Okay. Now, an exercise for you, obviously, is to try and look at this, use these things, plug it back into the embedding metric, and then you are and then you are home. Okay, so so then I mean, as I said out here, this particular thing is going to actually cover just a part of this I mean space-time, this particular highlighted portion. And so we are going to get another form of the metric. So what is the other form of the metric? The other form of the metric is this. Okay. So so you would see that what has happened is you have a du by u squared plus u times something, which is a flat metric, and there is an r squared which sits out in front. Okay. This is, so remember what we did earlier. You can actually put in some things about the yeah, okay, I think you can scale things a little bit. Okay, let's I mean, let me not get into that. So this form of, I mean, this form of the metric is something that so with a very sort of straightforward coordinate coordinate redefinition, you can actually go from 7.12 to the thing that I had written for you at the end of the last class. That is a metric that looks like this. Okay. So you see this guy and that guy would actually be I mean would actually be just related if you just you know, use a coordinate redefinition of you know, u as l u bar, something like that. Okay. So this is the metric that you're going to get, and in this form, you see what is very clear cut is that there is a subgroup of, I mean, ISO 1p that acts on this part of the, I mean, this part of the space-time, right? And this is just the isometries of, I mean, this is just the isometries, I mean, of the boundary. And so what is, I mean, so this becomes, this is the, I mean, Poincare transformations of x and t. So this is what is happening when you look at when you're looking at the putative boundary of, I mean, of the theory. So these are the Poincare transformations of that. If your x and t are going to label your boundary coordinates, this is what is going to happen. Okay. Now there's another thing as well, which is also clear from this, that there is an SO11 isometry. And this SO11 isometry acts at the following. It takes t, x, and u to ct, cx, and c inverse u. This is something that you can see from here. And as we also motivated in the earlier part, this is what is going to translate to the dilatations of the CFT in R p plus 1. Okay. So you see that the isometries of the bulk are mapping to the I mean, conformal symmetries of the boundary theory. So there is a mapping between the symmetries, the, I mean, isometries of the gravitational theory that lives on the bulk to the global symmetries of the field theory. Okay, of the field theory too. Very good. So let me try to give you a little bit more of what ADS CFT is in these last few minutes. Okay. So at least now we see that from the point of view of symmetries, there's a matching between this bulk theory in ADS P plus 2 with a CFT in RP1. Okay. We expect actually the partition functions of the theories to match. Okay. So you can write down a formal relationship between the CFT observables and the observables in the bulk theory, and this is captured by a proposal by Gubser, Klebanov, Polyakov, and Witten. And this states the following. I'll try and be a little clearer with this. I think this part of the thing is a little unclear, I mean, even in my terms. So it's going to say that the generating functional of CFT correlation function of some operator O, which is sourced by a current J, is equivalent to the partition function in the bulk theory, which is evaluated with boundary conditions for the corresponding bulk field, determined by setting its uh, boundary value to the source. I mean, of course, you didn't understand this. So what is happening is that there is some field in the bulk. Say, okay, now I don't know if I can add this. So let me try and do that. So let's do this. So there is some particular field. So I'm going to draw something which is a Penrose diagram, but I don't expect you to really, if you have not seen this before, I don't expect you to really understand this. But this is what is known as the Penrose diagram of ADS. I mean, this is the bulk. The bulk, if you wish. So your theory, if you wish, lives on the inside. Okay. So the theory is something that lives on the interior of this cylinder. And suppose there is some field here. Okay, there is some field here. There's some field phi. Okay, and if the field has a particular profile, and suppose you sort of take this out back here, so and you call this guy phi of 0. Okay, so what we are saying is that there is going to be some fields in the bulk, and which you can take to the boundary, and when you reach the boundary, these fields are going to sort of be the sources of some particular operators, say O, in the theory that lives on the boundary. So this is this CFT, if you wish, which lives on the boundary. So there are these operators O in the CFT that couple to these sources, which are like phi naught, and these are going to be added on to the usual CFT. So the CFT, what is going to happen is, if you write down the action for the CFT, so the action for the whole thing is going to be action for the CFT plus these extra operators, ddx of O into phi naught. Okay. So this is like adding some source terms to a field theory. So you have a field theory, which is your usual field theory. Let's, for example, So, and this is going to be sort of like interaction terms, if you wish. Okay. I'll clarify this a little bit more. Okay. Just give me a sec. Okay. Let's clarify this a little bit more. Okay. Now suppose let's try and make this thing a little simple. Now suppose inside of the bulk you have a field which is phi. Okay, phi, and this is a massless scalar field. What are we going to do? We are going to solve the Klein-Gordon equation. Okay, and we are going to solve the Klein-Gordon equation. So this is what your Klein-Gordon equation for your massless field looks like. Okay, there's no mass term as well. Now you take your Poincaré coordinates and you solve this equation. Okay, you solve this equation. I'm not going to solve it for you. I'm going to indicate the steps, and you take the near boundary limit. Okay, so that is u goes to 0. So if you do this, then what you're going to be left with, so this is an equation, a second order differential equation. It'll have two roots. All right, so the two roots are going to be so the phi is going to be some u hold to the d minus delta into phi naught, and the two roots, one of them is going to be delta equal to d, and the other is going to be delta equal to 0. So as what do you expect? If there's a profile, you expect things to usually die off, right? In your usual, usual electrodynamics, you don't, if you did not, so you always expected that at infinity your fields will die off. This is happening for one of the cases where say this delta equal to 0, where this, as u goes to goes to 0, that's where the boundary is. So that dies off. So that's a sort of thing that we call a normalizable mode. But there is also this other thing where delta is equal to d. So phi actually goes to something which is phi naught that does not depend on u. Okay. So it gives you on the boundary something that has not. So it gives you a constant at the boundary. So it has not died off at the boundary. So this is going to be acting like a source. Okay. So for example, what happens is that if you were to look at, so this was a massless case. If you were to add a mass term, things will slightly change, and you're going to get phi goes as u to the delta plus minus phi naught, where delta plus minus is given by this formula. This r squared is again the radius of ADS. Your small d is the dimension that you are in. Okay, very good. So that's what is happening, and so now, all right. So it's very natural to associate the dimensions, this particular delta, as a conformal dimension that is associated with this dual operator. And the other natural interpretation is phi naught is sort of like the source for an operator O that exists in this sort of boundary theory, and this will have the same representations of for the symmetric groups as well. Okay, this might be a lot to sort of take in at the same time, but remember, just try to remember what we are doing. We are saying that a theory of gravity in d dimension, in d, well, let's say d plus 1 dimensional anti-de Sitter space, is equivalent to a field theory, a CFT, that lives in d dimensions. To show you an example of this, what we are doing is we are looking at a scalar field. Okay, scalar field that is there in say inside ADS, and we are trying to see what we can do. So we are trying to solve the Klein-Gordon equation. So you have, it's not just so what we have done is there is gravity, of course, but there's also this extra probe, if you wish. A scalar field is there, which we have thrown inside the bulk. So what is it going to do? It is going to, if you take that as this, extra thing, so you will have to solve the Klein-Gordon equation in the bulk, right? So the Klein-Gordon equation in the bulk, you can solve that. Now you want to understand what happens when this particular field nears the boundary of ADS. And if you do that, you find that there are these two modes. Okay, if you're looking at a massless field, there is one mode which just sort of dies off, and you're fine. But there's another mode which does not, and that, in a sense, is doing something on the boundary. So on the boundary, this is acting like a source for another operator. Okay. So if you wish, the pure sort of gravity theory inside ADS was dual to the pure CFT on the field theory side. Now you've perturbed this thing on the bulk side with some scalar field. So there has to be an equivalent sort of perturbation on the CFT side as well. And what is happening is this perturbation on the bulk side is going to source the perturbation on the field theory side. Okay. So there is an operator O by which this field theory thing is going to be perturbed, and that is what the sort of map between the two says to us. Okay. And what we are saying is these sort of phi plus minus are going to be the dimensions of are going to be the scaling dimensions of the operator that is associated with this. All right. So you can so now let's just try to understand what is it from the point of view of the partition function of the CFT side. So as I said, there is going to be the usual CFT partition function, which is just the fields into the exponential of e to the minus s. But now there is this extra piece as well, so you have perturbed the bulk. So you have to put in some extra particular operator. This is something that you should have or should be learning in your field theory classes as well. So you can look at perturbations of this, and so you can find out what the endpoint function is in this way. For example, if you were to find out the endpoint functions of this CFT, what you're going to be doing is you're going to be taking the you're going to be taking the del phi phi naught xi's on this partition function, and you're going to be setting these things equal to 0. So now the ADS CFT correspondence boils down to saying that this partition function on the field theory side is equivalent to something which is going to be, so you are going to have certain boundary conditions, and there is going to be a partition function on the bulk side which also gives you the same answer. Okay. So on the bulk side, for example, if you were to look at the 2-point function, so now you know that if you have 2-point functions in this CFT, that is going to go like 1 over x1 minus x2 mod to the power twice delta. This is an exercise I wish I could do, but I can just give you a rough idea that you can look at the partition function on the bulk side, and you can, so this is related to things like the on-shell action, which you can do. So there is a very well-defined procedure that you can do also on the bulk side, and then you can reproduce the answers that you have on the field theory side by means of this mapping between CFT and ADS. Okay, so you can take functional derivatives, and you can find out what this would give you on the bulk side. This is a more involved exercise, but I would I would ask you to maybe go back and look at this. Yeah, unfortunately, this is far from ideal, in the sense that I wish I could have given you some more details of this, but at least you get an idea of it, right? So in the sense, what I wanted to show you in this class, I'm not sure if you guys are very confused or not. So the idea is, when you are thinking about the an ADS CFT, so what is a gauge gravity duality? So the first thing that you need to check in a gauge gravity duality is the fact that you would have the symmetries on both sides need to match, right? So we saw that, if you are thinking of ADS, the isometries of ADS are SOD2, and the same SOD2. So this is the isometry of ADS D+1. If you, for example, if you are in 5-dimensional antidissonant spacetimes, your isometric group is going to be SO42. Okay. Now we have seen before, and so the crux of the argument is that a conformal field theory in 4 dimensions also has global symmetries of SO42. So the isometric group of ADS and the global symmetries of a CFT in 4 dimensions are one and the same. Okay. So now, now, I've shown you with some particular choices of coordinates how this isometry. So, for example, how something like something like this. So if you were to look at something like this is going to be what happens in your in the bulk. On the boundary, this acts as this is just a scale symmetry that you're going to have. So everything including and of course the Poincaré, ISO 1P is also clear from here how it is going to act on the boundary theory. Trying to understand these special conformal transformations are a little more involved, but this is also something that you can do. So the isometries of the bulk map on to the global symmetries of the boundary theory. But ADS CFT is more than just that. It says that the partition functions on both sides also have to match. And because these partition functions on both sides have to match, what happens is that you can find out correlation functions of the CFT also from the bulk. Okay, you can try to do things in the bulk and you can. So there is a map. There is a very clear-cut dictionary, if you wish, between what is happening in the bulk to what is happening on the boundary. For example, you could have certain fields in the bulk, and they are going to correspond to some operators with specific operator operator dimensions on the boundary theory. One of them will source the other. This is something that I didn't say. For example, if you have just pure gravity, then you know that there are gravitons, the fields which are G mu nu. These are going to actually source in the CFT. These are not external operators, right? So you shouldn't have anything extra. So in a field, so this is something that every CFT should have, and indeed this is the stress tensor that you define on a CFT. So that is graviton in the bulk actually will source the stress tensor on your field theory side. There are more and more things that one can do, and this has been a tremendously active field of research over the past 20 years, and it actually does continue to throw up many surprises. We could have a year-long course only on this, so I am sorry that I've had to cram all of this up into just one lecture. But in the next lecture, what we are going to be doing is we're going to be focusing on 3 dimensions in the bulk, and I'm going to be showing you how again, I'll have to wave my hands a little bit because not all of this is something that I can finish in one class. Again, I'll try and give you some references and let you do that yourself. But I'll outline for you how you can get these infinite, dimensional symmetries of a two-dimensional CFT out of a three-dimensional ADS. And then we will see one of the uses, and we will end up with that. Okay. So I understand that this class was a lot of words, and I'll try and upload the notes as soon as I can. And I'll also try and give you guys some particular references. So yeah, so that was a long monologue. So let me pause for questions and drink some water as well. Okay, guys, time to wake up. So if you guys have any questions, yeah, please.
Yeah, like the boundary condition you choose, like is it, do you have choice, or like it is already fixed?
Yes, you do have a choice. Actually, okay. That's a very, interesting thing that you ask. Now, depending on what, boundary condition that you are going to pick, you might end up with very different sort of theories, So again, this is something that I will not be able to give you much of details on. But let me just say this, okay? So next time around, I'll just very briefly mention in the case of three-dimensional ADS what are called Brown-Heno boundary conditions, okay? So if you pick Brown-Heno like if you pick Brown-Heno like boundary conditions in three-dimensional ADS, which is the thing that almost everybody does, what you end up is with a sort of with symmetries which are two copies of the Virasoro algebra. Okay, so that is going to be, in a sense, the duality between three-dimensional ADS and two-dimensional CFTs. Now you could pick certain other things as well, whereby, so there is this boundary conditions by Lee Song and Strominger, with which you could pick up something entirely different. You're not going to get two copies of the of the Virasoro algebra anymore. You're going to get one, and there is going to be a U1 enhancement of that. So it does depend. So you are actually free to choose what sort of boundary conditions you want, and depending on that, your the theories are going to be dependent on that. So that's crucial, actually.
Okay, so yeah, even then, like since the theory is different, then you have to use a different partition function, and the correspondence still works.
Exactly. Yes.
Okay, and like one more thing, like I don't know, like many people who would have asked this, like why doesn't this work with DS? Like you use the isometry group of.
No, so the idea, the short answer is that some forms of it does work. No, now you can always propose that it works, right? And there are certain shortcomings with it. Like, so as I said, there is a way, there is, so you would say that a thing really works if you can, at least a part of the field that we work in is going to insist that, in order to make everything work, you would have to have, an embedding in string theory. Okay, trying to do that for the DS case has proved very problematic. Second thing is, what is happening is that if you look at the Penrose diagram, and I mean, if you are looking at ADS, for example, maybe I should have kept this on. Okay, let me see. Yeah. Okay, let's see. We have some space here. So the in this case, the holographically emergent sort of direction that you have is going to be this radial direction. Okay, so you can draw smaller and smaller cylinders if you wish, and you'll so this radial thing is the one which works well. Now if you have DS, the natural thing that is going to emerge is this sort of the time direction. Okay, and not so there is a rotation. So if you wish, the natural emergent direction in de Sitter holography is the time direction. So there things become troublesome. Okay. And the other problem, if you wish, is also embedded in a formula that I can show you here. It's fun that I actually wrote down this formula. So you see, there is this formula which I wrote down for you here. Okay. Okay. This is the conformal dimensions related to the dimensions of the field theory. The dimensions in which the theory lives in. So the bulk theory lives in D+1, and that's a relation. And there's this radius of ADS which sits here.
Right. Yeah.
Now, if you were to go to DS, for example, what you'll have to do is you're going to have to take R going to I times R. Okay. So this is a simple exercise that you can do. So you can take R to IR, and then you'll see that everything goes through. So you see that this sign is going to change.
Right. Yeah.
And after a certain, this particular thing is no longer, so under the square root, you're going to get some weird stuff, right?
Right.
There is going to be signs, right? So if you are going to look at a high enough mass stuff, your conformal dimensions of your dual theory will have imaginary pieces.
Right.
So things like bounds, what are sort of unitary bounds in your CFT, go for a toss.
Yeah.
This has been a very naive way of trying to look at it. But as we speak, there are people who are trying to actually work out what is the best way of looking at this. And this, R going to IR business is something that gives you some amount of the picture, but it will not give you the whole picture. There are the representation theory aspects of it is something which is not well understood. So there is more there. There are things, I've just told you about these highest weight representations. There are things called the principal series and so on, which actually make, there is much more there, actually. Okay. So this is something that is being understood. I think Dionysus spoke about it.
Yeah. He spoke
just a few days back, right? So yes, so that's the short short answer to all of this. But this is a good thing to ask again.
Okay.
Any more questions, guys? All right, let me try and stop recording.